Hi, thank you, Sarina, for the very nice introduction. I want to introduce to you my current project, exchanging water molecule in protein-ligand free energy calculation by Monte Carlo molecular dynamic sampling. So as we all know, binding free energy is easy to calculate from molecular dynamic simulation. We just calculate the difference between the protein-ligand complex to the components separate in solution. As long as our cavity is solvent exposed, we don't have a problem. If our cavity is buried, we'll find ourselves in a situation similar to this, which is obviously wrong, and where we want to be is here, where water occupy the cavity. So the solution we did is we performed translational water moves with Monte Carlo, which allowed buried cavities to be hydrated and dehydrated. To speed up the calculation, we define a steric grid where gray represents the atoms, dashed line the hydration shell around them, and everything that is covered by an atom or the hydration shell is considered inaccessible for water. That means we are trying to place water only in areas that are free. This results in us needing to perform a lot less energy calculations. Another optimization we performed, we focus on an interest in an area of interest. What does it mean? We don't really care about water exchange between bulk to bulk. This is kind of sampled very well in the molecular dynamics. We care about what happens in the protein-ligand complex within the interior. So we trim our simulation, our grid for the Monte Carlo from the 3 direction. We did extend it in the 1 axis into the Z. We did extend our grid for the Monte Carlo into the Z axis to allow some bulk water to exchange, because we assume that the first and second hydration shell water might be more difficult to move. So we kind of extended it into the bulk. And the way we did it is we just implemented our Monte Carlo code into the Ember MD package. It's available already since Ember 18, also in the current Ember 20. A bit about the outline of our program. We perform n number of MD steps. Then we enter our program marked in blue. We build the steric grid. Then we choose a random water and a random destination. We calculate the energy and perform the Monte Carlo criteria. If it is rejected, we just go to the next step. If it is accepted, we update the coordinates of the water molecules and the coordinates of the grid. And then we keep on doing this until we reach the predetermined number of MC steps. Once we reach this number, we go out again and perform the MD. In order to check that our method is working, there are 2 criteria we have to obey. First of all, we need to allow water molecule to exchange in and out of buried cavities. And 2, we want to yield a correct Boltzmann distribution. So we created a very artificial system with 2 graphene walls that don't allow water to penetrate. If we perform MD, obviously nothing happened. If we perform MCMD, we can see that water can cross the barrier and occupy the middle region. If we're looking at this graph, red is the density in the outer region, blue is the density in the inner region. We see that densities go up and down correspondingly until they equalize between the 2 regions. The next thing is a thermodynamics test system, which we built, again, a very artificial system, low density water, 500 K, which is pretty much steam. The purpose of this system is to have a very high acceptance rate for MC, because if we generally just try MC, the acceptance rate is so low, it can be within error range. In our current system, our acceptance rate is about 45%, which is a lot, which means the MC has a significant impact on the total energy. And what we could see is very nicely that red is the energy of MD. green is MCMD, averages are the same, distribution is the same, everything looks good. So this is kind of our previous paper. We published it in 2019. The conclusion of this part is that MCMD is able to place water molecules in a thermodynamically correct manner in solvent inaccessible cavity, and the number of water molecules can change during the simulation. The fact that it is thermodynamically correct leads us to our next step, which is this allows us to use our method in binding free energy prediction, which is the next step. So as we all know, binding free energy, as said, we calculate the difference between the protein-ligand complex to the components. And in a classical thermodynamic cycle, we just do a relative binding free energy. We convert ligand 1 to ligand 2, but the difference is that this perturbation results in the change of the hydration state. In order to test the ability of our method to be used in binding free energy calculation, we built a data set that we had 4 requirements. 1, we want to have a buried cavity. 2, to have at least 2 similar inhibitors. 3, to have different number of buried waters between the different ligands. And 4, we need to have experimental data for these ligands. So let's have a look at one example. Ligand W1, we convert it to ligand W2, changing the hydroxy to methoxy results here in the displacement of these 2 water molecules. And the way the pipeline, or the way we did our calculation, we did it, the perturbation in 3 steps: decharge, van der Waals, recharge, brackets, the number of windows, or the number of lambda windows in each step. We calculated both directions. So we convert ligand 1 to ligand 2 and ligand 2 to ligand 1. And we repeated the calculation 5 times. This pipeline is taken from Silicon Therapeutics, our collaborators in the project. We see here, of course, the perturbation from the one direction will be exactly the inverse of the perturbation in the opposite direction. Now, the graph is a bit busy, but let me take you through it. So we performed 4 different methods. We start in all of them from the protein-ligand crystal structure. For methods 1, 2, and 3, we remove the crystallographic water, we solvate and set up the window, and then for method 1 and 2, we perform an equilibration using MCMD. In this equilibration step, everything is restrained except for hydrogen and water molecules, which means that if needed, the water molecules can occupy their place in the buried cavity. Then we performed for method 1, TI using MCMD. For method 2, we do TI using only MD. Method 3, we did the equilibration using only MD. So if the cavity is inaccessible, the water molecules cannot go in. And then we did the TI using MD. Method 4 is a bit different. In method 4, we kept the crystallographic water, and then we performed everything the same. What does it mean? It means that if we are converting ligand W1 to W2, we will start with these 2 water, and in the opposite direction, we will start without these water molecules. The take home, or what we want to remember from this slide, methods 1 and 2 are MCMD, method 3 and 4 are only MD. And this kind of leads us to the point of this method, because if we are converting in different lambda windows, at some point, or the windows are of course independent, and we want to place the water molecules, but we don't know how many to place. So we start from ligand W1 and we end at ligand W2. On the left is the number of water molecule at the end of the equilibration step, averaged over the 5 simulations. And this is kind of, again, the important point, because we see the first and last window might be easy to tell because we know that we need to have 3 and 1, but we see that what we don't really know what to do in the middle windows and how to determine the hydration state in each of the windows. So we kind of let the MCMD do it. And here, when we look at the results, we see that we start from around 3. And along the simulation, we go down and end at about between 1 and 2. On the opposite direction is the window of W2 to W1, which is projected in the opposite direction. So we just see the exact same number of water. A dashed line represents the standard deviation, and the numbers are just the averages. If we are looking at the right, we see here is a running average of the number of water molecules during the TI window. And we see that the numbers during the TI windows are very similar to the numbers at the entrance to the TI window. So the equilibration step pretty much determines the number of water molecules. It can change slightly later, but this is kind of the important part that determines it. Another important thing, why is this important? Because we could have cases of partial water density, especially in the middle windows where water could be equally favorable in and out of the cavity. The fact that we're repeating the calculation 5 times, we assume that in such a case, the repetition will represent it, and in some of the cases, the water will be in, and in others, the water molecule will not be in. And in the total average of the energy, this will be taken into account and lead to correct calculation. Now for the results. First of all, as always, we check the hysteresis of the perturbation. This is a very fancy equation, but if we go back here, we just see that we kind of sum the two numbers. If the value is 0, it means that the hysteresis is 0 and the simulation works very well in both directions. It just means that both directions get the same value. And this is very interesting because what we can see is that methods 1, 2, and 3, not completely surprisingly, kind of expectedly, leads to very low hysteresis. It means that the back and forward simulations are very similar. These are the 9 perturbations we had in our data sets. Not very surprising, method 4 leads to very high hysteresis because, as we said, we start with different number of water for each direction. So it kind of creates a mess, and this leads to very high hysteresis. And now let's see how we work with relative binding free energies. So then we compared our numbers to the experimental data. Here it's also very interesting to see that methods 1 and 2, which are doing MCMD both, are kind of similar and have very low values, around 1 kcal per mole. Method 3 and 4 are both not doing well, with RMSEs of 3 to 4, kind of high, kind of not succeeding. There are a few very interesting things to see here. First of all, if we look at specifically W1 to W2 in method 3, so the hysteresis, I'm back one slide back. If we're looking at the hysteresis was 0.0, but 7 kcal, almost 7 kcal difference from the experimental value. So the back and forward were very similar, but completely wrong in both directions. So just looking at the hysteresis is not enough. Another thing that is very interesting, that if we're looking, many of the simulation, even if we don't consider the water molecule at all, work quite well. And this is actually in agreement with literature, where it was in multiple cases shown that water does not need to be taken into consideration, which is kind of strange and not very intuitive. But if we think about it, if a water molecule is equally happy in its cavity and in bulk, then taking this water into account does not necessarily matter for the relative binding free energy calculation. So this is very interesting to see that the source of the error is from a few perturbations that fail miserably. Method 4 again leads to high numbers. This is from our last paper, which was just accepted last week, and it is currently in press. It's not yet online. Now there are a few things I wanted to show or focus about. When I did when I check the structure of the HSP90 or FCQ, there are in the crystal structure 3 buried water molecules, 1, 2, and 3. When I simulated my program, I very consistently only occupied 1 and 2, and water molecule 3 was never occupied. Looking at the electron density, or what we see here, we can see that water molecules 1 and 2 has a very clear and defined electron cloud representing them, whereas water molecule number 3 has like it looks like a contamination on the ligand, because it seems like just something is growing out of the ligand. So maybe a contamination in the ligand resulted in electron density here that resulted in placement of water molecule. So speaking with the crystallographic friend, they told me something like, as a crystallographer, I don't care if I'm putting water in or not, you know, it doesn't matter for me. And I'm like, okay, for me, it can kill my calculations. So that's a very big deal for us. So it's always kind of another advantage of using our program, that we kind of just trust ourselves and not add any additional source of error to our calculation. So this is very important. Something else that I wanted to discuss, we had another perturbation that we determined as an outlier, and I want to show it because I think it's very interesting. So the KEK, it's a tripeptide, glutamic acid changed to tryptophan, and we see that whereas experimental value is 0.1 kcal per mole, the all 4 methods resulted in about 15 kcal per mole error. So there are 2 main reasons that could cause for such wrong numbers. One is if we are not placing the water molecules correctly, and 2, if the TI calculation is just not working. So what we did is we checked, first of all, how our water placement looked in compared to the crystal structure. Pink is the crystal structure. Here is when the first lambda windows of the KEK to KWK mean it's still fully glutamic acid. And on the right is the last window of the opposite direction perturbation, means again, it's fully glutamic acid. And what we see is that the water molecules are very perfectly placed, nicely overlapping. Looks like the water placement works well in this case. On the bottom is the opposite direction of the perturbation of tryptophan to glutamic acid. And again, we should see that 2 of the 3 water molecules are very correctly placed. One is not exactly placed, but looks close enough, to be honest. And this leads us to think that the water placement succeeded, and the problem is not the water placement, but probably some kind of force field issues. Also, the fact that all 4 methods fail in a very similar way leads us to think that it's not an artifact or a fluctuation or something. It's a very systematic error, probably. Our guess is the force field.
Sorry, 1 minute left.
Perfect. So to conclude, MCMD samples the hydration of buried sites in a thermodynamically correct manner, and it was successfully used for relative binding free energy calculation, resulting in low hysteresis and high agreement with experiment. With that, I want to thank, first of all, the collaboration from the first project, Charlie, Lynn, Ross Walker, and Tom Kurtzman, which led us to the next collaboration, which I would like to thank Shishon Lin, Charlie Lin, Brian Raddak, and Woody Sherman from the amazing collaboration in silicon therapeutics. And of course, my PI, Mike Gilson, and the entire Gilson group for an amazing environment. And with that, I want to thank the committee for inviting me and you guys for listening. Thank you very much.
Thanks a lot, Ido, for the nice presentation. So we have a couple of questions, and I was asked to read also the names of the people that asked the questions. So the first one is from Debarati Dasgupta. And the question is it absolutely needed to do 5 or more than 5 TI runs to have enough confidence in our simulations? You specified 5, so was there that an arbitrary choice? Also, for absolute free energy calculations, how do we assess the convergence of the TI runs?
So I tried 5 just because one, it was the pipeline that Silicon Therapeutics usually used. I wanted to make sure that I'm kind of consistent. I did not see huge differences between the 5. So I cannot say 5 is enough, 5 is not enough. I guess it's very much system dependent. So if the system fluctuates, it might not be enough. If the system is relatively stable, it will probably be enough. So this, I just did not try less. For absolute binding free energy, it's kind of more problematic because what I saw, I actually started doing it, and what I saw is that most absolute free energy cases result in, so I did see that our program was able to place it, to properly place the water, but I did not see an influence on the absolute free energy. So I don't know how to say. So this is something we are still checking. I cannot say how to best do it for absolute free energy.
Okay, thanks. Then the next question is by Jacob Littman. Have you found any advantages to method 1 versus method 2? Using the MCMD solvent placement only as an equilibration step makes it easier to incorporate into other workflows.
We were thinking about it. To be very honest, I did not see huge advantages for method 1 over method 2. I think, again, the starting, if we start with the correct water placement, then we will be doing good. So to be honest, the results of method 1 were better than method 2, but I would say within error range. So I would say if we are doing the equilibration step, it's probably sufficient.
Okay, thanks. Then we have a question by Niels Hansen. Very nice approach. I have 2 questions. What is the ratio between MC trial moves and MD steps in between the MC phases? Is the orientation of the water molecule optimized in the MC insertion?
So the orientation is not optimized in the MC. The reason for that is we kind of assume, since we choose random water, the random water will have random orientations. And then once they are placed, they can optimize themselves in the MD. So the MC will just be to place them. So we did not account for orientation of the water molecules in the placement. And as for the ratio, in this step, the MC is significantly more than MD. I think I did 100,000 MC to 100 MD, but the MD here is pretty much meaningless because just for, again, hydrogen and water. And in the next step, I did it 10 to 1, so 10 times more MC than MD. But again, I did not try to optimize the method. It was more as a proof of concept that it's working. So I kind of did a lot of MC steps on purpose. I think it can be reduced, it can be optimized, especially with knowing the system. Kind of, if you know this, we have found in our previous paper that kind of we had the major urinary protein and the cytochrome C peroxidase, that the difference in the hydrate in the buried cavity required in the CCP 10 times more steps than in the MUP. So accordingly, if we know the system, we can account for it in the relative binding free energy. Here, all systems were kind of blind to me, so I just did it very extensively.
Okay, thanks a lot. So in the interest of time, we can unfortunately not do additional questions, but there are additional ones in the Q&A. So please, Ido, if you can afterwards answer them directly in the Q&A. So thanks again for the presentation. And then if you can stop sharing, we would move on to our third speaker of this session. So let me introduce Max Ebert. So Max, can you share maybe already your screen? So Max studied